and should be talking about visible and invisible searches for sub-GeV dark sectors.
Okay, so it's working. So good morning, everyone. As Gabi said, I'm going to present a little bit about visible and invisible searches for sub-GeV dark sectors. Is it work okay? Okay. No, that's okay. 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 So, firstly, I would like to introduce a little bit about what I'm looking for, the light-dark sector. So as we know, for dark matter, we have to have certain characteristics for it to account for dark matter itself, but we have a huge variety of mass range that we can work on and propose many models. One of the most famous ones up until now in the last decades was the WIMP, due to the WIMP paradigm and due to the fact that it was a really natural proposal, as it would be generated by, its abundance would be generated by a thermal relic of the Big Bang, just like all the other particles, and via freeze out, etc. Thank you. But as we also know, the colliders and all the research, most of the research was focused on the WIMP, and up until now we didn't see anything, which caused the parameter space to be highly constrained. So this open opportunity to other types of models to increase its popularity, like the light-dark matter, that has the same characteristics, the same the basic characteristics like as WIMP. So it is a thermal relic of the Big Bang. It is neutral and electrical and color charges, and its abundance is via freeze out. But as we are dealing with a lighter mass, we have to include another particle, a light mediator, because if not, it would generate an overabundance of dark matter in the early times. So we end up with a dark sector and not just a light dark matter itself. So we introduce, as I said, a light hidden mediator that would connect the dark sector, the dark matter, with the standard model particles. So in this case, the dark matter doesn't have a coupling to the standard model itself, but it has a coupling to this dark mediator, which couples to the standard model. So in my case, I'm going to be looking for sub-GeV dark matter, which is in the range of MeV to up to 1 or 10 GeVs. And in this prospect, one of the best experiments to look for this type of particle is the Na64, which is a fixed target experiment. So it works with a beam of the SPS, electron beam from the SPS with 100 GeV, and it is It works in a lower energy due to the fact that we are looking for a lower mass particle. So we don't need, and actually would be worse if we look for higher center of mass energy. So explaining a little bit about its construction. So we have the electron beam that has 100 GeV, and this blue shaded regions, we have the objects that we have to reconstruct and get the energy of the particles, the beams. So we have some trackers, scintillators. Here we have magnets that will deflect the beam, causing it to radiate in synchrotron radiation. and that will account for a more clean view for this signal, because if we have any other particles, it will deflect in a different way. So here we are assuring that we are only passing electrons with certain energy through this other part here. And here we have more trackers, the detector for the synchrotron radiation. And here in this green part, we have the target, the active target, that is also electromagnetic calorimeter. So here, the beam will interact with this active target and interact with the nucleus, producing bremsstrahlung or an annihilation. And then we have a series of hadronic calorimeters to ensure that we see nothing. So what we look for in this kind of experiments is no signal. If we measure something here, that means we imagine some hadrons that were produced after, and what we want to see is missed energy. So it was constructed to look for the dark photon initially, but we can look for a huge variety of mediators and dark matter types with this kind of experiment. So in our case, we propose a scalar and also a pseudoscalar, but here I'm just showing a scalar mediator that has a universal coupling to leptons, and also that couples to dark matter, to fermionic dark matter. So in this part, if we put this coupling to a higher value, we can look for visible signals of this decay that we can constrain not with the Na64, but with other experiments that collides electron-positron beams like Bell. And if we introduce this fermionic dark matter and this coupling, putting this coupling to a higher order, we can look for invisible decays in dark matter with the help of Na64 to constrain the parameter space. So the two major processes that we look for is the nucleus scattering of the electrons, with the electron with the nucleus of the active target, and which will produce a bremsstrahlung-like radiation of this scalar mediator or any mediator that can decay in dark matter or in leptons. Important thing that I forgot to mention is that in this case we have a leptophilic scalar, so it only interacts with leptons. And we can have also an annihilation, a resonant annihilation that will produce the dark matter of leptons in annihilation. So in this plot, this is using the Na64 as a simulation to address what we consider a signal. So we have 100 GeV beam initially of electrons, and for the Na64, they consider a signal if we have at least 50 GeV of missing energy. So this would correspond to this band, this yellow band right here. And the y-axis here we have the energy that were detected in the hadronic calorimeters, and the x-axis we have the electromagnetic calorimeters. So in this band right here would be mostly most of the energy was detected, and here in this band, as we can see, you have from 0 up to 50 GeV that we get in the electromagnetic calorimeter. That was where the beam initially interacted, and we have nothing in the hadronic calorimeter. So just this band, if we got any signal in this band, would be considered a signal of dark matter. So this is the kind of plots that we can have, and the kind of constraints of the parameter space that we can produce with this analysis. In this case, is a prospect of the final plot. So We are constraining the type of dark matter and the mediator. Will produce this curves that represents the relic abundance curve. So in these cases, what we did a little bit different as well from other cases is that we are considering a different ratio from dark matter to the dark mediator. Normally, they only put this to 3, so the mass, I don't know if you can see, but the mass of the scalar is equal to 3 times the mass of the dark matter particle. Here we consider other types of other cases. So we have this this type of curve due to is dependent on the annihilation cross section that it also will be constrained by the right amount of abundance that we have. This bumps right here is due to the production of also muons and other particles. Before that, we had only electrons because we didn't have energy enough. We also put these bands reference to the G-2 of the muon. But as we've seen recently, I didn't put the paper here, but this uncertainty was largely killed or excluded. So it wouldn't be a band, it would be a curve. So in the case of the bell, we are constraining the visible search of dark matter. So in this case, we have a Bremsstrahlung or annihilation that produces this scalar, which will decay into leptons. And in this case, we are also looking for a bump and an abundance of the production of these leptons, and this bump would have the center of it and the mass of the scalar mediator. So we are here we consider universal coupling, but it was already looked for in other works, the coupling, a normal coupling to depending on each lepton flavor. And in the case of Na64, we look for it including a fermionic dark matter that will result in an invisible decay, as I said. And normally when we consider this case, we impose that at least this ratio have to be 2. So the mass of the scalar has to be at least 2 of the mass of the dark matter, because we want it to decay in the dark matter. And we normally put this coupling as higher as possible to impose that we are producing mostly the dark matter and not other particles. So as we can see, if we get in the case of the 9 ratio between the scalar and the dark matter, and also the 6, this dotted one, it can constrain, the Na64 can constrain a little bit of the parameter space in the lower order of mass, but it stops here in the 1 GeV scale. So it's interesting to observe as well that the Bell and Na64 can, in a way, complement itself in this analysis. So I don't know how I am in the time. Oh, I'm okay, because, yeah, so in conclusion, I think I got a little bit faster. So in conclusion, what I wanted the message to be is that light dark matter in the sub-GeV range is a good way to look for dark matter, a new model that we are not so much focused on, that we were not so much focused on up until nowadays. The Na64 is a new experiment that it's continuing to increase in its popularity and importance, and can be a really great experiment to look for these types of dark matter, like dark photons or scalars or pseudoscalars. And that we can use also other types of experiments that are still running in a different perspective, like Bell, but to complement this analysis on light dark matter. So it's basically, thank you.
Questions? I guess we have a shy audience today. Okay, thank you very much, Leticia, and we have a coffee break outside.